Hello, this is Rolf. Welcome to the video lecture series on the course of Design of Steel Structure. This is the lecture number 8 on the unit number 4, that is Design of Compression Member. So in this video lecture, we are going to see about the types of sections used as a compression member, what is a build-up column, what is a lacing for build-up column, and what is a batten for build-up columns. Let's start with the types of section used. The requirement for compression members are more demanding than those for tension members because of their load carrying capacity is the function of shape as well as the area and also the material property. Thus, the member must be sufficiently rigid to prevent general buckling in any possible direction. It should be from any possible direction. The member should sufficiently prevent the general buckling. An ideal section is one in which the same moment of inertia about any axis through its center of gravity. So take this and it is your center of gravity. So any section that is passing through the center of gravity should have the same moment of inertia. So any section that is passing through the center of gravity will have the same moment of inertia. So according to that, the rolled steel sections are preferred. Why rolled steel sections are preferred is, so for a same unit weight, rolled steel section cost less than the build-up sections. That's why we are going for the rolled steel sections. In the rolled steel sections, there are different types of sections available. That is, I sections, channel sections, tubular sections, rods and bars, angle sections. These are the different types of sections that is available in the rolled steel sections. Let's see one by one which section is used. So if you take rods and bars, these rods and bars can withstand very little compression. So when your length is more, it can withstand very little amount of compression. So we cannot use this for a longer length. So these rods and bars are recommended for length less than 3 meter only. 3 meter only we will recommend this. Second one is tubular sections. These tubular sections are most suitable for small loads and lengths. For small loads and lengths, same as like the rods and bars. These sections are usually provided for roof trusses and abrasing. These tubular sections, we are not using it for for past few decades. We won't use this tubular section because of the difficulty in connection in the riveted or the bolted connection. But due to the advancement of welding technologies, nowadays we are using these tubular sections also as a compression member. And if you take the single angle sections, these single angle sections having a less radius of gyration when it compared to the channel and the I section. So hence it is not suitable for a long lens. So we won't use it for a long lens. So for a long lens, we will use channel section or I sections. We will use mostly channel sections will be used as the compression members. So these angle sections will be commonly used as stud in roof trusses with riveted or welded connections we will use. Suppose your compression members are designed for a very large structures and carrying a very heavy load, then we will use build-up sections. So build-up sections will be used when we are designed for a very large structures or very heavy load. We will go for the build-up sections. Build-up columns. So build-up column is, so when the rolled section do not provide required sectional area, or when a special shape or a large radius of gyration of column, so we will fabricate a build-up sections. That means, so if your available sectional area is 1200 into 10 to the power 4 mm square, assume it is, okay. So it is your sectional required sectional area. But in a market, you are having 1000 into 10 to the power 4 mm power square. So only 1000 is the maximum, but here we need 1200. So we will go with the two section. We will combine the two section and to achieve the required sectional area. That type we will call it as a build-up section. Or if any special shape we require, then also we will go for the build-up sections. Usually these build-up sections are provided by either lacing system or batten system. So lacing system means if it is a column, so this type is a lacing, and batten system is this type. We will call it as a batten system. So why we need the lacing and battening for build-up columns? So the different components of build-up sections are placed in such a way that the build-up section has same radius of gyration about the axis. So for that we are using the lacing and battening system. Second, the different components of build-up sections are connected together so that they can act as a single column. And the third point is the lacing and battening systems are used to connect members. It's used to connect the members. So where we will use the lacing and where we will use the battening system? So in case of eccentric loading, we will go for lacing system. If it is an axially loaded member, we will go for battening system. Lacing for build-up column. So what is the general specification for lacing? So angle, flats, angle, channel and tubular sections are used for a lacing member. Second point, the lacing system should not be varied throughout the length of the member. That means the length of the lacing system should be same, and what system you are using, whether it is a single laced or it is a double laced, it should be same throughout the length of the member. Third point is the single lace system on opposite side of the main component should be the direction so that one will be the shadow of the others. So if you are using the single lacing system, so if you are using this direction as shown in the diagram, if you are using this direction, the opposite side also you will use this direction. In opposite you can't go like this, you can't go like this. So opposite also you have to go in this same direction. And the fourth point is tie plates should be provided at the ends and at the points where the lacing systems are interrupted. So this is the tie plate, and here also we will provide the tie plates. These tie plates are used to connect the lacing system with the member. So these are the general specification of the lacing system. We will see what is the design specification. First one is the effective slenderness ratio of laced column should be increased by 5%. That means, so if your normal slenderness ratio is 10, means it is increased by 5% to 10.05. Why we are increasing the 5% means to account for shear deformation due to unbalanced horizontal forces. Due to the unbalanced horizontal forces, we are increasing the 5%. Next is the angle of inclination. So the angle of inclination of spacing with the horizontal axis. So this is the horizontal axis. So the angle of inclination is this one. This theta should be between 40 to 70 degree. 40 to 70 degree, not more than 70 and not less than 40. It should be lies between 40 to 70 degree. The slenderness ratio of the lacing bar should not exceed 145. It should not exceed 145. 45. Next parameter is what is the effective length of lacing member. So for a single lacing system, so this is the single lacing system having the bolted or riveted connection, the effective length is equal to the length of the lacing member. So if it is a double lacing system like this, your effective length is equal to 0.7 into length of the lacing member. So for a welded lacing, your effective length is equal to 0.7 into length of the spacing. So how we can find the longitudinal spacing? This is the spacing, length. Length is the spacing between the two the lacing. So how we can find that one? So this L can be find out by L by RC minimum less than 50 or less than 0.7 times of KL by R, whichever is lesser. Whichever is lesser. From that we can find the L value. RC minimum is the minimum radius of gyration. Minimum radius of gyration. So what is the minimum width of the lacing bar? The minimum width of the lacing bar is depend upon the shank diameter of the bolt and nominal diameter of the rivet. So according to that, if your shank or nominal diameter is 22 mm, then your width is 65 mm. If it is 20, it is 60 mm. If it is 18, it is 55. If it is 16, it is 50 mm. So that we can say the width of a lacing bar is approximately 3 times of nominal shank diameter of the bolt or nominal diameter of rivet. So we know the minimum width of the lacing bar. What is the minimum thickness of lacing bar? So the minimum thickness of the lacing bar is, we can find out by, if it is a single lacing, T minimum is length by 40. If it is double lacing, length by 60. So assume it is a 1000 mm length of the lacing bar. T minimum is for single lacing is 1000 by 40, that is 25. If it is for double lacing, 1000 by 60, this 16 by 66. So this will be the minimum thickness of lacing bar. So after the minimum thickness and minimum width and all, now we have to calculate the shear force, transverse shear force. So how we can find the shear force? Shear force is, this shear force is designed to resist the transverse shear. So V is calculated by 2.5% of design axial load column as per the limit state design principle. And this is same 2.5% of axial load column if it is in the working stress method. The lacing should be designed to resist additional shear due to bending if the compression curve is bending moment. So if the compression curve is a bending moment, it should be designed to resist the additional shear also. So how we can find the forces? So assume this is one of your lacing. So this lacing will have the force. Due to the force, you will have the nominal reaction, that is V by 2N. So how we can find the F value? So F value is V by N into sine theta, because it is an inclined angle. It is in incline, so theta. So F by V, F is equal to V by N sine theta. So for a single lacing, N is equal to 2. So this formula is equal to converted into V by 2 sine theta if it is in a single lacing. If it is a double lacing, F is equal to V by 4 sine theta. For double lacing, N is equal to 4. So this is the design specification for the lacing of built up column. Let's move to the batten for built up column. So what is the general specification for the batten? The number of batten should be such that the member is divided into not less than 3 parts longitudinally. That is, minimum 4 batten plates or minimum 2 intermediate battens and 2 end battens should be given. So totally 4 batten plates we have to given, 2 may be intermediate or 2 may be end plate we can given. For using the battens, we will prefer flat plates. So flat plates are used as a batten system. Here the effective length of the batten column should be increased by 10%. So but in lacing system it is increased by 5%, but in batten system it is increased by 10%. So what is the design specification of the batten? First one is the spacing of a batten. So see, this is one batten and this is another batten. What is this spacing? What is the spacing between the two battens? So how we can find the spacing between these two battens? This can be found out by C by RC minimum less than 50 or less than equal to 0.7 times of KL by R, that is the slenderness ratio, whichever is lesser. From this formula, we can find the spacing of the batten. So RC minimum is minimum radius of gyration of the compound, and S is the transverse distance between centroid of bolt group or rivet group. So that is, this is the bolt or rivet group. So from the centroid to centroid distance is S, transverse distance, and C is the spacing of batten, and LB is the transverse distance between centroids of inner end bolt group or rivet group. So inner, so from here to here, what is that distance? That will be the LB. So from that we can find the spacing of the batten. Second design specification is this batten should be designed to carry bending moment and shear force arising from a transverse shear. So we have to calculate the bending moment as well as the shear force. So first we need transverse shear V. So how we can find the transverse shear V? Same as 2.5 times of axially loaded column in case of design axial loaded column in case of limit state method, and 2.5 times of axial load column in case of working stress method. From that we can find out the longitudinal shear force. So what is the longitudinal shear force on batten? V1 is Vc by Ns. So V is transverse shear force, C is spacing of batten, N is number of parallel plates of batten, and S is the transverse distance between centroid of bolt group or rivet group. So from that we can find the longitudinal shear. Second, we have to find the bending moment on batten. M is equal to Vc by 2N. Vc by 2N. So here in the moment we don't have the transverse distance between the centroid of bolt group or rivet group. So this is how we will find the longitudinal shear and bending moment on the batten. Next is thickness of batten. So the thickness of batten should be greater than the length of batten blade divided by 50. So length of batten blade divided by 50. The thickness should be greater than that. Okay. Then what will be the effective depth of batten? So for intermediate batten, D should be greater than 3A by 4. What is the A here means? A here is from center to center from the flanges. So this is the A. And for end batten, D should be greater than A. For any other batten, D should be greater than 2 times of B. So what is the B distance? B distance is width of the flange. So this is the B distance. So overall depth of batten is equal to effective depth of batten D plus 2 times of its distance. So this is the overall depth of the beam batten, and it is the design specification also of the batten. In this video, we covered what are the types of section that will be used as a compression member. So what is the built-up column? What is the design specification of the lacing? And what is the design specification of the batten? So by this, our unit number 4 is completed. Thank you.